Hello students, myself Professor Ankur. I welcome everyone for the GATE theory session on analog circuits. Today we are going to cover important topic second order active filter and instrumentation amplifier. This is our fourth session from the main topic of operational amplifier. Let's start with the session now. So in the previous session, we have already seen the impact of first order low pass filter where we had an op amp and the feedback at the inverting terminal with the resistances RF and R1 controlling the gain. And now when you can see resistor and capacitor in this circuitry, you will find back to back two networks which are having the same component features. So there will be a resistor capacitor pair which will be used back to back so that we can go for two-stage filtering. And from that we derive the term called as second order low pass filter. So the second order low pass filter is basically a better version of the first order low pass filter, where instead of using one RC filter we will be using two RC filter, and because of this we get a better gain roll off of approximately 40 dB per decade compared to the previous case where the roll off was only 20 dB per decade. The cutoff frequency of this filter will be defined as FH and it will be controlled by the component values R2C2 and R3C3, whereas RF and R1 will actually control the gain of the system. So now when I see the value of VO, it will be AF into VA, where VA is the node voltage of the non-inverting terminal of the op amp. AF value is 1 plus RF by R1 and VA is the voltage at the non-inverting terminal. We will get VO by Vin on solving the equations or with respect to the KCL points at the input section where the Vin is being connected, as well as at node A. The value will come out for VO by Vin as AF divided by S square plus R3C3 plus R2C3 plus R2C2 minus AF R2C2 into the entire thing into S divided by R2 R3 C2 C3 plus 1 upon R2 R3 C2 C3. Now when you compare this equation with our standard second order Butterworth transfer function, which is going to be A divided by S square plus 2 zeta omega ns plus omega n square, where omega n is basically the cutoff frequency of the second order filter. From that we can conclude that the value of omega h will come out to be 1 by R2 R3 C2 C3. A is defined as the overall gain, zeta is basically the damping factor, and omega n is actually defined as the natural frequency of oscillation, which according to the second order filter concept is our cutoff frequency. So on comparing with the standard function, we get the value of omega n square as 1 upon R2 R3 C2 C3. So automatically omega h will have the value under root of R2 R3 C2 C3. So your FH will be 1 by FH will be actually 2 pi FH square will be equal to 1 by R2 R3 C2 C3. From this you will get the value of FH as 1 by 2 pi under root of R2 R3 C2 C3. Now we are going for some standard assumptions where we can take the value of R2 and R3 equal to R and C2 and C3 will become equal to C. Under this situation, the value of the cutoff frequency will become 1 by 2 pi RC. The DC gain of the passband will be 1 plus RF by R1, and for the second order low pass filter, that value is approximately equal to 1.586. So we are actually having the impact of damping factor, which is 3 minus AF by 2. So 3 minus AF by 2 is considered to be 0.707, where you get the value of AF as 1.586. So now when you put that value in the equation of gain, 1.586 will be equal to 1 plus Rf by R1. So Rf by R1 will come as 0.586. So Rf will be automatically 0.586 times R1. If you take the standard value of Rf as 10 kilo ohm, you will get the value of R1 as 10k divided by 0.586. You will get the value of R1. If you see the response carefully, at the cutoff frequency, we are landing up at the 3 dB point, and the slope of the response will be much more steeper with a slope of minus of 40 dB per decade compared to the previous first order filter slope, which is minus of 20 dB per decade. So this is the major advantage of using a higher order filter. A higher order filter will always give you a better response, and under this situation, a practical response will always try to approach the ideal response. Now, when you go for the magnitude of VO by V in angle phi, that will become your function as VO by V in. In the S domain, the VO by V in of S can be defined as AF divided by S square plus 3 minus AF by RC into S plus 1 upon R square C square. This equation was derived assuming that all resistances and the capacitances of the filter component section are actually same, or you can say matched values. Now, when you go for the second order high pass Butterworth filter, in the previous section we have already discussed the first order low pass and first order high pass, where we have came to a conclusion that by swapping the position of resistor and capacitor, we can land up at the low pass to high pass conversion or high pass to low pass conversion. So here you can see the second order high pass filter is having a similar arrangement with only one change. The capacitors are in the input path and the resistor is at the ground path. There is a feedback, there is a small amount of positive feedback coming from the output via your resistance R2. On similar lines, when you can see the response carefully, the response will be looking with respect to the function of AF and 0.707 times AF, where AF is basically defined as your passband gain, which will have the value 1 plus RF by R1, and the cutoff point will be defined as FL. The voltage gain versus the frequency response can show you clearly that we are starting with the stop band and approaching the pass band. The maximum gain will be AF and the cutoff point will be at 3 dB down, which will be at 0.707 times AF, which will give you the lower cutoff of the second order high pass filter. The value will be approximately equal to 1 by 2 pi RC, because we are going to assume R2 equal to R3 equal to R and C2 equal to C3 equal to C. And the value of your AF, which is the pass band gain, which will be again 1.586, which is the similar gain that we have seen in the second order low pass filter. So automatically RF will become 0.586 times R1. So if your observation is sharp, you can just swap the positions of the passive components filters. Automatically we can jump from low pass to high pass and high pass to low pass, because the frequency calculations are going to have a similar relation and the gain is going to be fixed in both the cases, which will be 1.586. Now we are going for an important amplifier, which is called as instrumentation amplifier. So an instrumentation amplifier is basically a difference amplifier where we are using it for practical application. This amplifier is realized using 3 op-amp circuitries. An instrumentation amplifier can be realized using 1 op-amp, 2 op-amp and 3 op-amp. So here we are studying the best possible instrumentation amplifier, which is realized using 3 op-amp. The initial 2 op-amps A1 and A2, where the inputs V1 and V2 are connected. If you see the feedback path, you will find the resistances RF1, RG, RF2, and the output of the both amplifiers A1 and A2 will work like an input to the third stage. So in this stage, you are having the amplifier A3 with the input points at non-inverting and the inverting. But because of the resistance pair R2 and R1, the actual relation we can derive as a single stage difference amplifier if you assume the voltage values at the node points of R1 and R2. The output will be R2 by R1 times the difference of the input given to the third amplifier. So now the main thing is how the output is getting produced by taking the inputs V1 and V2 into consideration. The final equation for the circuitry output will be R2 by R1 into twice of RF plus RG upon RG, that is as good as R2 by R1 into 1 plus twice of RF by RG into V2 minus V1, where V2 was the input given to the A2 amplifier and V1 was the input given to the A1 amplifier. So this is the relation between the output and the difference of the input of the instrumentation amplifier. In many industrial applications where we are actually using physical parameters like temperature, humidity, water flow, so we are going to use transducer circuitry to measure them, and the output of this transducer are required to be amplified, and that is supposed to be done with the help of instrumentation amplifier. So it is basically a practical amplifier circuitry used in practical applications. Now, the advantage that we get from this circuitry is we are going to have a variable RG, which will be useful in varying the gain of the system. And the biggest advantage that we get is the gain of the entire system depends on the external components, that is our resistor. So as and when we require variation in gain, we can modify the component values. Apart from that, they also provide a very high input impedance, a very low output impedance. And now since the CMRR is going to be very high, this amplifier is going to be very useful. So if the CMRR is very high, then you will be able to get better performance or optimum results. So an instrumentation amplifier using 3 op-amp is one of the best packages circuitry which can be realized using 3 op-amp elements with a combination of resistances to process difference of input in practical industry application. So this is the entire concept of instrumentation amplifier. In this session, we have gone through the second order low pass filter, the second order high pass filter, and the instrumentation amplifier using 3 op-amp.